So I'm going to start off by talking a little bit about who Lucid are. You may not have heard of us. There's no penalty for confessing that. Where we come from, and then a little bit about what our project is, which is birthed in what we see, our vision for the future of personal mobility. And then I want to explain a little bit about some of the simulation tools and the organizational approach we've taken to developing the vehicle that we're working on as far as we have. So we describe ourselves as a startup company, but in truth we've been around for about 10 years, so we're probably like the aging dad with the tank top at the disco, still claiming to be a teenager, but really we've been around for 10 years. And we started out making battery systems primarily for the Chinese market, for public service vehicles, buses out there. And we did that sort of fairly successfully. And during that period, we started to develop other powertrain concepts and technologies. And so then we committed ourselves at about the end of 2014 to actually bringing this all together into developing a new range of all-electric vehicles. Some highlights along the way. One that I'm particularly proud of is that back in 2016, we were awarded the contract to design a new Formula E battery pack. So with our partners McLaren, who are doing the trackside support and logistics, and Sony, who will supply the cells to us now, Murata, we developed the pack and all the software that supports the pack based on our technology. Where are we now? Well, we're currently closing our Series D funding to head towards production. So I'm hoping, even when I get back to the office on Thursday, that the final ink will be on the paperwork for that. But we're certainly very close to that now, and then about 2 years away from production. So let's talk about where the idea of our particular electric car came from. And I'm going to do this by doing this traditional thing of looking into the future, into the crystal ball of my imagination. And we've seen some of that already this morning, where that crystal ball can take us. I think there's two opposite dangers when you look into the crystal ball about the future. One is that you imagine that everything's going to be the same, that nothing's really going to change. And then the other extreme, you've got this, particularly where you're considering technology evolution, you have this idea that everything's going to be completely different. And so I want to start off by putting a sort of a cautious word in there about this vision of the future. And I'm going to take a quote which I think might even be a biblical quote, which is, I think the original quote was something like, "Where your treasure is, your heart will be," which I guess is a way of saying where you spend your money, that's probably what you care about. So if we look at the 5 things that apparently we're told that people spend their money on, they're things like, for example, the house we live in. So this is my little pad up the road at Chatsworth. Our families, if you have children, you will know how expensive it is. And if you are a child, and I think we all are, you should feel guilty about that. Our education and our retirement. So 5 things that we spend money on, which show where our heart lies. Actually, the 5th thing is the car. The car is just massively important. And why is that? It's in the top 5 things we spend money on, personal transportation. It's partly because of the value we place on getting places, so on the travel. And it's partly because the car is actually an expression we use it as an expression of our personalities. So just like that hack rod, that fantastic hack rod presentation earlier on from Mouse, was all about how people use cars to express their personalities. That's not going to change. We put so much passion and energy into that, it's not going to go away. So that's a point of continuity. We expect that as we look at the future of technology, the car will remain important as a personal expression. So having said that, let's look at some of the drivers that are going to generate change. One of them is clearly electrification. So a lot of people are talking about that. There's a lot of money going into that. And let's call a spade here. This is not about high costs of petrol, okay? I've learned to say gas now because of but I'm just translating it back to my native tongue. It's not about the high cost of petrol. This whole country could be floating on a sea of unrefined crude oil, and it wouldn't change the fact that we need to go to a different mode of transportation. In all probability, petrol isn't going to cut the mustard for that. It's going to be electrification, I believe. And that's because of the ecological requirements of making our world continue to be a livable place. So I think now over half of the human population lives in cities. That's a trend that is continuing into the future. And these cities, if you look at a photograph of Beijing or Delhi or Athens or I don't know, Sao Paulo or some of the cities in the States, you can see that through that fog of pollution that we need a new way of motorizing our transportation. And the millennial generation is said to be the first generation that's actually willing to pay a premium for that. So there is a recognition that in the next generation, or the current generation now, I'd say, of consumers, that green transportation is a requirement. So it's not an esoteric thing anymore. So it's coming along. It's going to happen. It may come in waves. It may come in a sudden tsunami even, but it's going to happen. Autonomy is a thing that is going to happen. I don't think it's going to happen as quickly as some people would expect or hope. I think it's a very complex issue, and we're all aware today of the news from the States about pedestrian fatality in front of an Uber car. That it's a very difficult problem to solve. I will believe it's fully here when I see autonomous cars driving through the streets of Delhi, but or perhaps even getting onto the Coventry Ring Road. But autonomy, the move in that direction is going to happen. The sensors are there, the actuators are there, the IT is there to move us systematically that way. Connectivity. We expect to be connected and to have a pervasive information flow that moves with us as we move from different context to context. We expect that, and we will increasingly expect that in our vehicles. And ride sharing as well. And I use ride sharing to mean all these other ways that we will gain occasionally or frequently personal transportation. So I, for example, in the States, a bit weird, I don't actually have a car for the first time in my adult life, and I'm experimenting with, well, what does it feel like to use Lyft and Uber and Zipcar and so on, to work out, what these per use or other ways of sharing transportation actually feel like. So these are all technology drivers, but bearing in mind that we have this passion as well to express ourselves through our car, we need to merge together those pictures of technology with this kind of spirit and emotion of automotive as well. So where at Lucid we take that is to try and boil it down to these three distinct pillars in our vehicle. So we call them energy, space, and time. So energy is obviously the ride, the vehicle dynamics, the performance of the vehicle, but then space, this a new expression of luxury, and then time, this ability to use the time that you're in the car in productive ways or to be connected to other data sources or other ways of making use of the time that you're in the vehicle. Now, we've tried to take that into some more tangible expression of what we mean, and the starting point has been this idea of a personal executive jet, so something which has a lot of luxury and has a lot of space inside, and obviously you don't think, hopefully you're not thinking about the powertrain particularly, but it's got the ability to get you there, but it gives you this cosseting experience. And how does that become possible? We see that becomes possible primarily because of the reduction, the miniaturization that electric powertrains bring. So if you go through the last kind of 100 years of power sources, you get to a very, very much smaller expression of the powertrain. The right-hand end, that little blob is a representation of our rear powertrain. And the significance of this is a lot of the traditional car is actually taken up with powertrain technology. And if you see that shrinking down, that gives you the opportunity to do other things with the space to redistribute it. So you end up with a vehicle which has very different necessary external proportions, and you can put in place features inside that really enable you to do other things with the space. So it's a bit like a TARDIS. You've got a lot more space inside than you'd expect in a more compact external form. That's a picture of our first vehicle, the Lucid Air. And if we take Mercedes as a benchmark, if you imagine something which has the exterior size of an E-Class, the interior space of an S-Class, and then something of the emotional style of, say, the CLS, you're trying to bring all those things into one vehicle. So it's a really very compact vehicle compared to others which have comparable space, so it's much more suitable for an urban environment. There's no compromise on performance, and you've got this new kind of luxury inside. And this, as I say, comes about because of the packaging opportunities of the miniaturized powertrain. So that's shows some of the rear seat accommodation and how it's wrapped around the rear drive unit. And then that leaves this space inside for the occupants. So you've got an experience of great luxury inside in what externally is a relatively compact vehicle, but without compromising on performance. So these figures are a little bit out of date now, but 2.5 seconds, 0 to 60. So hopefully that would be okay for Mouse. I think you can cope with that. We're really limited at that point with tyres, but maybe some of the more distinctive things you see at the quarter mile will be under 10 seconds for the quarter mile, and well over 400 miles of range. So that number on the right-hand side is going up all the time. So we get a lot of performance out of the vehicle. This was a track day last year where we took it up to 235 miles an hour, which is a very exciting thing for us. Now, we obviously will speed limit the car. We don't expect people to be driving around at 235. And only those with a strong constitution will do 0 to 60 more than once or twice in less than 2.5 seconds. But it's just an illustration that the powertrain, although it's small, isn't compromised in performance. So we mentioned energy, we mentioned space, this new expression of luxury. And then autonomy. Now, we're a relatively small company, at the moment around 350 people, so we're not going to be writing a fully autonomous software suite. That's a very demanding technology. But we are equipping the car with all the sensors and actuators to be fully level 4 autonomous. And we're providing a base level of driver assistance and autonomous capabilities. And then we'll deliver full autonomy over time as it becomes reasonably and safely available through partnerships. So the car will be fully autonomous ready with all the sensors and actuators for level 4 autonomy. So how are we going to get there? Or how did we decide to get there? I want to say 3 things about simulation, which I think frame this for me. The first thing is that, I'm quite an old guy now. I can remember simulation, I don't know, 30 years ago, when the miracle of simulation was actually accuracy. And that's really a journey we've been on, trying to get to a point where our simulations are accurate over, a very long period of time. And that's very exciting. But now we've got to take that as a given, okay? If we can't make accurate simulations now, there's something wrong with our understanding of the physics. So accuracy, we have to take as a given. And if we're not there, we have to look at ourselves and work out why not. Now we need to go further and say, well, it's not just about the ability to predict what the vehicle will do or what the subsystem or component will do. It's now, we now need to make broader decisions about what we do with that accuracy. So I would say then 2 things. One of them, the first of them, is design space exploration. This idea of all the things that we could do, how do we somehow programmatically explore every aspect of the design space that we might be able to occupy. And that's one of the really exciting things about those pictures of generative design that Mouse was showing earlier on, or indeed I can't remember, was it Element, the software that we saw just now? This idea of actually populating a physical structural space with any conceivable design and allowing the physics then to guide you to what the optimal design is for whatever parameters that you're looking for. And I'll talk a little bit about this later on, but just to illustrate, this idea of design space exploration has been responsible for improving the power density of our inverters from our first generation, which was 8.3 kilowatts per litre, to our current inverter, which we're just working on finalising at the moment, which is at 40 kilowatts per litre. And all of that improvement in performance, in power density, in powertrain miniaturization, has come from design space exploration. And then the second of my two kind of reframing of simulation points is multi-physics. Now, I love this phrase here, which is a good Californian phrase. It's from a Scotsman, actually, who then made his life out in California, John Muir. And he said famously, when we try to pick out anything by itself, we find it hitched to everything else in the universe. And I sort of take that as a lead-in to say, if we take any area of physics, whether it's structural analysis or whether it's thermal analysis, the previous generation of simulation, we looked at those items in isolation. Now there are many situations where you can't really properly understand the performance of a system operating at the limits of its capabilities without linking those areas of physics together and simultaneously considering them. And so we take design space exploration and multi-physics analysis very seriously at Lucid, and that's a core way we've set up our simulation technique. So let's look around the car and see how that translates into reality and how we've tried to achieve that. So the first thing I would say is we take our initial look at how we would set our team up. Obviously, is based on, we know we've got to design all these subsystems in the car. And we started out by saying, well, look, let's have a multi-physics team who are responsible not just for multi-physics, but design space exploration, and a technology evangelist to try and draw in all the other teams into seeing this virtual development process in the way that I've just been describing to you. So, for example, we have obviously a battery team. That's a core technology for Lucid. We have a transmission team. Those, by the way, are my powertrain responsibilities, but we're very closely linked to the HVAC team and the aero team and suspension and vehicle dynamics. And all these blue dots represent groups of engineers who are working together on their subsystem. And one really important thing, a visionary thing, I think, from our CTO, Peter Rawlinson, and has worked very powerfully for us, is to recognize that real simultaneous engineering really requires you to be co-located with the people working in systems that are related to your system. And in a vehicle, that's pretty much everything. So we all work in one area, in one building certainly, and mostly in one physical area. And we're arranged physically in the room next to the people with whom our systems are interacting. And that's a very powerful organizational paradigm. So you make everybody responsible for understanding the full role and interaction of their system in the vehicle. And even those last grey dots on there, the supply chain team, are distributed through the actual engineering design team to make a single integrated simultaneous engineering organization. Then we looked at, well, how are we going to do this virtual development process that we're aiming to make our vehicle, base our vehicle around? Obviously, we use many tools. I want to talk about some of them that are particularly important for the multi-physics analysis, design space exploration, that we based on using ANSYS technology. So we started out with a relatively small group. So obviously, multi-physics was leading that. We did our external aerodynamics with Fluent. We did all the cooling technology, particularly powertrain cooling, was done directly by the multi-physics team. And then we had a battery team looking at various areas of technology. And as they started to work on that, that evangelism process rolled out and other teams started to come on board. And obviously now we're starting to use more licenses, more different technologies. Particularly, we brought on board then the electromagnetic simulation for the motors. We brought our first HPC cluster. And this process continued through 2015. As we needed a second cluster. This is a product of actually getting aerodynamicists involved in simulation. You never have enough cores, I'm afraid. So we gave them one of their own to keep them out of the way. And then as that continues, we were then starting to use cloud service analysis. And so we had a huge overflow from our in-house HPC, and we started to explore cloud analysis in various ways. And then beyond that, we're starting getting into HFSS and antenna design and so on. And at this point, we've now got a very good arrangement now with ANSYS, where practically we've got virtually unlimited licenses across the organization. Just give you some illustrations of the kind of analysis we've been doing. Here at the moment, here you're seeing some of the work we did early on the airflow to the heat exchangers at the front of the vehicle. And this thing we call the Lucid Vortex, which is about how do we efficiently spread air out over the whole surface area of the heat exchanger with a very narrow air inlet at the front. So this was an early part of our aerodynamic study and our thermal analysis. So this, we call it Lucid Vortex, but it's been a very neat part of the development of the vehicle. Another example, I mentioned the electromagnetic analysis. This has been real core to developing this miniaturized powertrain. So the ability to use Maxwell to do very accurate and well-integrated predictive analysis. And in this case, these were our induction motors. These were our first generation motors. Last year, we finished the development work on our new generation of permanent magnet motors, which we've also developed by basing our analysis on Maxwell. And both for the induction motors and now for the permanent magnet motors, we're able to use the models. They're sufficiently accurate that we can actually do all our motor control software development in a virtual world as well. And that when we take it onto a dyno, the motor control software is working straight out of the box, as it were. So we're getting predictive accuracies of 1 to 2% at worst in our motor predictions. And we've reduced our dyno calibration time by 80% by focusing on building a deep understanding of the physics into our analysis. I want to talk a little bit about multi-physics. This is a nice example of taking some simulations from Maxwell and working out loss maps in the motor and then pasting those as heat sources into the motor analysis. And here we were trying to look at the effect of oil spray cooling on the end turns of the stator. And we were doing iterations between the thermal analysis and this complex fluid analysis. So this was very computational intensive. And here ANSYS were very supportive in facilitating the development of those fluid phase models, which we could iterate back into to actually resolve the distribution of temperature in the motor to a very high degree of accuracy. So those models are very complex. Even the one in the middle is quite complex. It's got a very sophisticated anisotropy in the end winding orientations and so on that are crucial to getting an accurate simulation of the temperature distribution. And then we can take that data back then into the mechanical analysis and the fatigue analysis of the motor. So that loop really involves a range of different physics types, but has been very important in helping us to get to the kind of motors we have now. So again, we've got temperature predictions within 3%, and it's taken our motors up a further increase in power density over 10%. So that was a very useful cycle. I mentioned that we'd come back to this design space exploration. One of the real issues with power electronics is extracting heat. Every 10 degrees centigrade of extra peak temperature in your power electronics halves the life expectancy due to thermal fatigue. So we wanted to work out how to extract heat efficiently from our system. What shape should you make your heat extraction cooling tubes? What internal features should you put in? So we developed a system where we could parameterize every feature of the design of these cooling tubes and the way they're fed. And each dot on the chart in the bottom left-hand corner is a different design. And then we allowed genetic optimization to explore all the possible designs within that parameterized design space to come up with our final design concept. And that enabled us to package it very, very tightly in the vehicle, but with very good performance. So we managed to bring our peak temperatures down by nearly 20 degrees. We're using discrete devices. We got all the temperatures of all the discrete devices down to a very narrow band. So it was a very successful analysis for us. And then we're looking at also the battery pack, looking at analysis of both the current distribution, the thermal performance, and the wire bond stability. And again, that was all done by different aspects, in this case of the ANSYS toolkit. Really, again, I want to emphasize the need to feed this from the deep physics And we have a partnership with Stanford Linear Accelerator Lab, where we can do 3D X-ray tomography of the inside of batteries in real time as the crystals are being charged and discharged, and the lithiation and delithiation process, to look for ways of managing our batteries to preserve cell life and to optimize fast charge performance. Mechanical analysis, again, we're doing very detailed and complex mechanical analysis of all our components, and right down to the very design of the teeth, but also up to the whole powertrain assembly. And it's very important to remember in these cases that we're not just living in a virtual world. These things have to be tested. So this is a couple of weeks ago, we were torturing our rear transmission just to try and, we're taking it through our whole sort of validation test sequence. That was a failed test series, by the way, because at the end, the last test on the series, the instruction on the test sequence to the driver was test to destruction. And unfortunately, he destroyed the tires before he could destroy the transmission. So there's a very high degree of reliability that we can place in the analysis that we're doing. And then there's a little bit here on antenna design. This was comparing blade antenna to planar inverted F antenna for the little shark fin aerials at the back, but we also did a lot of work on, for example, GPS antennas. So this is a new area that we're going into. And then finally, all these things that we're looking at are the things I've been describing you might call component or very detailed analysis, but clearly there's a layer above that where we need to then start looking at how those systems then interact with each other. And so we have a whole new layer of modeling on top of that to actually enable us to look at these system interactions. And we're looking at Simplora as one of the ways of aggregating those together. And we have some very successful, in those graphs on the right there, you can't really see the details, but we have some very successful whole vehicle systems modeling now that enable us to do things like, for example, do virtual simulation of the Nürburgring and look at, for example, battery performance as it depends on the thermal interactions and the power demands from the motor and so on. So this is just one example. This is a nice example because we can actually run this as a pre-programmed cycle on our dynos and validate that it's actually performing in reality as it did in the simulation. Then looking to the future, the big thing obviously, or one of the big areas to explore is the autonomy, and that's very much a sensor data analysis driven thing. So there's a whole set of models that we're developing to deal with that. So obviously we've got the real world itself, and then we've got the detailed interaction with the real world from the sensors, and then we've got all the data processing from that sensor data being fed into the actuators, into the vehicle itself, and then back through vehicle dynamics, back into the driving in the real world thing. So that vehicle system model, we're not fully there, but that's where we're going at the moment. If you look at what that represents in reality, clearly there's a huge amount of data to collect in the real world, and we do a lot of cloud data collection and analysis out on the roads. But then we have some high-fidelity sensor modeling tasks to complete, which are all about very detailed simulation of how sensors interact with the environment, as well as using some of that data then to automatically generate richer data sets than we can gather through the limited amount of driving inevitably you can do. So we want to have a much bigger data set. So we're doing a lot of simulation work, or working towards simulation work to do that. And then a big part of our vision is real centralized collection of difficult real-world scenarios then, enriched by those simulations to do sort of cloud-based validation for our continuous improvement of our vehicle artificial intelligence. So this is a slide which really is a journey that we've just started upon, but we can see particularly some of the ANSYS tools that we're using are going to be very powerful aids to us going down that route. So just summarizing all that, I would say that my conclusions from an analysis viewpoint is obviously developing any vehicle, an electric vehicle no different, is very challenging. A core part of doing that is to have a very strong hierarchical, so able to operate at different levels of component up to system, simulation environment. I think it's very important to think about design space exploration rather than just testing whether this bright idea or that bright idea work. You need some systematic way of exploring that design space. I think you need multi-physics analysis in many parts of that because you can't get to the accuracy you need if you just deal in single physics domains. And so in all those areas, we've been fortunate really to have a good partnership with ANSYS in exploring their tool set. And I think the word partnership is very easy to say and very hard to do. And we've certainly, I think, probably more than any other of our software tools, been very pleasantly, not surprised, but enjoy very much a real partnership, which has given us very flexible access to a very diverse tool set and a lot of support required. Because if I was going to say anything negative to ANSYS, it would be, write some better documentation. But so you need a lot of support to do a lot of these things. But the tool set is very competent and very rich, and we've been fortunate to have a real partnership in developing it. So I hope that's Jenny. Jenny likes to be the last person in all our slide deck. She's one of our designers, relaxing in the rear seat of one of our first cars. So I hope you've got an idea about our vision of where we're going, and also, critically, I think, for this presentation, how systematically we've been trying to get there through using these advanced simulation techniques. So thank you very much for your attention. Very happy to talk to anybody afterwards. I'll be around during the day about what we're doing.